Oh, good afternoon, everyone. It's a pleasure to introduce our speaker, Ron Donagi, who will tell us about products of matrices, non-abelian Hodge theory, integrable systems, and 3D mirror symmetry. Ron?
Well, thank you, Philip, and thank you, Ludmil, and the organizers for this nice conference and for the invitation. So the work I'm talking about, I would like to emphasize an aspect of it, which is basically pure Hodge theory, although the motivation and most of the work is actually coming from some problems in physics. So let me try to set up the context. So given a collection of conjugacy classes, let's say C1 up to Ck of matrices and SLN, the Deligne-Simpson problem asks whether there are matrices representing those classes whose product is 1. Simpson solved this problem under the assumption that one of the classes, let's say the last one, is regular semisimple, or regular in general. He showed that in this case, the solution exists if and only if two numerical conditions hold. Here, so one is that the sum of the dimensions is bigger or equal to this magic number 2n squared minus 2. The other condition is that the sum of some defects is bigger or equal to n, where Ri denotes the minimum rank of the matrix AI minus some multiple of the identity. In other words, it's just the total rank n minus the maximum number of Jordan blocks with any one eigenvalue. So you look at the eigenvalue that has the most number of Jordan blocks or the highest geometric multiplicity, and you subtract that. So one goal of this talk is to propose a possible extension of this to the case where none of the classes Ck is regular semisimple. On that condition that one of the classes regular semisimple is essential to Simpson's approach. And the inspiration for this comes from physics. So I'm going to make a very long detour through some physics and hopefully come back to this towards the end. So the physics has to do with three-dimensional mirror symmetry conjecture, which predicts that n equals 4 supersymmetric theories in 3 dimensions come in pairs, such that the A twist of one is equivalent to the B twist of the other. You don't really need to know what those words mean. I'm just going to try to give the general impression. These theories have moduli spaces that basically have two branches, which are called the Higgs branch and the Coulomb branch. And these are supposed to be interchanged by this duality. An important source of examples is, and the only one that I'll consider, is furnished by these theories of class S. So these are obtained from a 6-dimensional theory by compactifying it on a Riemann surface with punctures. And then the dual theory is a certain quiver gauge theory. I'll call it S dual. The works of some physicists and of some famous mathematicians give an example, give an explicit construction of the Coulomb branch for this dual theory, S dual, which is the Higgs branch of S. The other branch, so that's the Coulomb branch of S or the Higgs branch of the quiver theory, turns out to be the total space of the Hitchin fibration associated to the theory. So that's where Hitchin fibrations come into the story. So we explore some aspects of superconformal field theories of this class S and the related tamely ramified normomorphic Hitchin systems. A key geometric ingredient is the construction of a family of Hitchin systems over the entire Deligne-Mumford compactification. And we'll then come back and explore the connections to the Deligne-Simpson problem in the behavior of these cowboy theories. And everything I'm talking about is joint work with Ashwin Balasubramanian and Jacques Dissler. And I'm told that this is not very legible, so my apologies. I'll read everything out loud and then I'll add some writing. So let me just repeat the problem. We're given conjugacy classes C1 up to Ck in SLN. The question is whether there exists representatives A whose product is 1. Of course, an equivalent way of formulating it is take the product from 1 to k minus 1, the matrices and have that be in the kth class or the inverse of the kth class. And basically Simpson tells us that the answer is yes if there's a condition, which is that one of the classes is regular semi-simple, and the sum of the dimensions is at least 2n squared minus 2, and the sum of these RIs that I explained is at least n. Well, the existence of a bunch of matrices is equivalent to existence of a local system on P1 minus k points, whose monodromy at the ith point is in the conjugacy class of CI. So you specify the monodromy or the monodromy conjugacy class at these points, and you ask, is there a local system that realizes this? And the big idea is to use non-Abelian Hodge theory, which was developed by Simpson and others in the compact case and extended by Simpson to the open case in dimension 1 and by Mochizuki to the open case in higher dimensions. So roughly speaking, this story says that local systems are equivalent to Higgs bundles. Then you have to add a bunch of adjectives. So you have to, in the open case, you have to consider filtered local systems and filtered Higgs bundles. And you have to make some assumptions on the degree in the case that on the first and second Chern classes. But in the case of a curve, you just need to know that the degree is 0 and you need some stability condition. So let me not get into too many of the details. But one key step in Simpson's solution is that he introduces a game that I will call a Simpsonos. It's kind of like dominoes, but your basic building bricks have various sizes. So assume that one of them has size n, and there's k of them all together. And so you have k batches. In each batch, you have a bunch of blocks of various sizes that add up to n. And the question is, can you rearrange them in a way that produces a winning solution? So what's a winning solution? You take this arrangement of Simpsonos and you assign to it a graph. So you start, so the graph has n steps. In this case, it'll have 8 steps. And the rule is that the difference of slopes at each of the n corners is going to be given by the number of connections above that. So the blue lines denote the boundaries of the blocks. And within any block, all the dots are connected. So you look at one of the spots, like the first one, and you see that above it you have 3 connections between the dots. And the rule is that you take the number of connections minus 2, and that's going to be the difference of the slopes. So the number of connections is 3, minus 2, you have 1. So that says that if the slope here was 0, the slope here will be 1. In the next spot, you now have only 1 connection. 1 minus 2 is negative 1, so the slope goes back to 0. So in this particularly simple example, the slopes are going to be 0, 1, 0, 1, 0, 1, 0, 1. So then you draw a big line connecting the initial point to the final point. You say that you have a stable solution if the graph is strictly below this line. So this is, in this case, we do not have that. We have a semi-stable solution because we're not crossing above the line, but we do touch the line. So a winning position would be something like this, where you stay strictly below that line that connects the initial point to the final point. The slope of the initial interval doesn't matter. I took it to be 0, but you can take it to be any integer slope. It will just rotate the whole picture by a certain amount, but it will not affect the question of whether you're above or below that line. So the question is well defined. So let me point out that there's a necessary condition, which is that the slope of the last line better be bigger, strictly bigger than the slope of the initial line if we're going to be under, if we're going to have some concavity, if we're going to be under the line. So that says that the total number of jumps must be positive, bigger than or equal to 1. And considering that you lose 2 steps in each at each corner, that says that the number of connections must be bigger or equal to 2n minus 1. A connection is one of those black lines. So Simpson's theorem says that assuming that the top block has just one block of n dots, and assuming this necessary condition that the total number of connections in the remaining blocks is at least n, so that altogether you have 2n minus 1 because you have n minus 1 in the top block, then there exists a stable winning position with one exception, and that's exactly the one in this example. Of course, this example has n equals 8. You can do this for any even n, I guess. So this theorem is a purely combinatorial result, which is tedious, but you just crank it out. And let me focus on how that's connected to the geometry. So the geometric translation of this Simpson's game is that you can build a particular kind of Higgs bundle on P1 minus those points. And it's filtered and stable and so on. In fact, there are some results of Wilfred Schmidt that tell you that this condition that the top row is just one block, which is equivalent to the previous condition that one of the conjugacy classes was regular semi-simple, implies that the Higgs bundles that you get will be variations of Hodge structure that are given the sums of line bundles. So you get line bundles because you have a maximal unimportant block there. And then by applying non-Abelian Hodge theory to this Higgs bundle, you convert it to a unipotent local system. The reason you get unipotent is because that's what corresponds to Higgs bundles. If you wanted to get non-unipotent things, you would have to have Higgs bundles with some non-obvious filtrations, and that makes it a little harder to construct. So instead, you do a first pass where you prove the theorem for existence of local systems in the case that all the conjugacy classes are unipotent. And then we go to the general case where we remove the unipotent assumption using deformations. So the key notion here is the notion of a sheet. Let me try to explain that. So, so if you have a Lie group or a Lie algebra, let's say Lie algebra G. So if you have a Lie algebra G, you fix the dimension of a conjugacy class. And you look at the disjoint union of all classes of a fixed dimension. And you take so a sheet is by definition a connected component of this union. So we'll stay with the case of SLN. And in that case, the sheets can be explicitly described, and it's actually a very pretty story. So we have the regular sheet. That's the case that dimension of the centralizer of the matrix is as small as possible, which is going to be, well, I guess I'm doing SLN, so it'll be n minus 1. In GLN, it will be n. then so it could look like a single Jordan block, or it could look like a diagonal matrix, as long as the eigenvalues are all distinct. And then it turns out that there are various other classes in between. And I'm going to try to describe for you how to get all of them. But the conclusion is going to be that every sheet contains a unique nilpotent or unipotent, depends whether you're working in the algebra or the group. So there's a unique unipotent class and a unique semi-simple class in various classes in between, and they're all connected to each other. So let me just illustrate what happens in the case of SL3. So what could a matrix in SL3 look like? It would look like ABC, where A, B, and C are three distinct eigenvalues. Or it could look like A, B, where A and B are distinct. Or it could look like a multiple of the identity. Or you can start deforming it. So instead of this matrix was AA, you can go to a non-trivial Jordan block here with an AA and a 1, keeping the B. Or starting with this matrix, there are two things you can do. You can have a 2x2 block followed by a 1x1 block. Or you can have a single 3x3 block. So altogether, I would say there are 6 types of orbits in SL3, and I've just described them all for you. And let's state the dimensions. The diagonal things are clearly regular, so the dimension is 6. And in fact, the 3 top examples are all regular, so they have dimension 6. The next 2 are going to be subregular. The dimension will be 4. These orbits are always symplectic manifold by Kosten-Kirillov, so the dimension is always even. You'll never get odd numbers. And in this case, the dimension is 0, because it's just anything that's conjugate to a multiple of the identity is that multiple. So these are the dimensions, and you see how they are arranged in sheets. So there's one sheet consisting just of the identity, another sheet consisting of these 2 types, and the third sheet consisting of the 3 regular types. You see that in each sheet, the left extreme is semi-simple, the right extreme is regular, is unipotent in the sense that all the A's are equal. If we're in SL3, then A better be 1 or a root of 1. Okay, so how do we describe these things? The easiest way to encode them is in terms of some partitions. So the partition in this case is just going to be 1, 1, 1. So we have 3 eigenvalues, A, B, C. We need a partition of 1 for each of them. So there's not much we can do here. In this case, in these 2 cases, we have 2 eigenvalues. So the partitions so we can have the partitions 2 and 1, or the partition 1, 1, and 1. 2 and 1 corresponds to a block of size 2, followed by a block of size 1. Well, here we have 2 blocks of size 1, followed by a block of size 1. And similarly, in the third column, the codes are going to be 3, 1, 2, and 1, 1, 1. So the number of columns in each case is going to be the number of distinct eigenvalues. And within each column, I have a partition which denotes the distribution of Jordan blocks for that eigenvalue. Okay. So the trick is you combine this collection of partitions in each case into a single partition, which is the associated uniportant partition. So this is just a general collection of partitions. You get a particular uniportant partition where you just add things in rows. So you have a 1, 1, 1 that gives you a 3. We have a 2 and a 1 that still gives you a 3, and so does this 3. But here, think of these as dominoes or Simpsonos. So you have a 1 and a 1 that gives you a 2 and a 1 above it. And here you also have a 2 and a 1 above it. And here you have a 1, 1, 1. So this is a little machine that takes a bunch of partitions, sums them up horizontally, and gives you a single partition. This single partition exactly determines the sheet type. So we see that two things are in the same sheet if they're in the same row in my picture, and I get the same partition here. In fact, it's easier, it's advantageous to look at the dual partition. So if you have a partition, you think of it as a Young diagram, where you're reading things horizontally. You get the dual partition if you read them instead vertically, count number of dots in columns instead of rows. So the 3 becomes a 1, 1, 1. The 2, 1 becomes again a 2, 1, but I'll write it horizontally. And the 1, 1, 1 becomes a 3. So the secret here is that the U partition describes for you the unipotent class in the given sheet, while the S partition gives you the semi-simple class in the given sheet. And the magic formula is that if you take the, so let's say the number here is our ni's. So the sum of the ni squared is the dimension, the centralizer of your matrix, which is n squared minus the dimension of the orbit. So in case you didn't know this, this is the formula for the dimension of the conjugacy class of any matrix. You do this little algorithm, you get a particular partition with numbers ni. So here you have a 3 that you square that, you get a 9. 9 minus that is 0, so you get the 0. 2 and 1 gives you 4 and 1, that's 5. So the complementary dimension is 4. 1, 1, 1 gives you 3, the complementary dimension is 6. Anyway, the relevance to our situation is any conjugacy class C is an equidimensional deformation of a unipotent one. And we've already observed that non-abelian Hodge theory gives you solutions in the unipotent case. And then by deformation and a few extra arguments, you get a general solution to the Deligne-Simpson problem under this one assumption that one of the classes is regular. All right. Are there any questions? I'm going to switch to the more physics stuff. So, as I was explaining, our motivation, our inspiration comes out of these questions about Hitchin systems that arise out of the physics of superconformal theories of class S. So the Hitchin system itself, I think everybody here knows it, but let me remind you very quickly. It's a global version of the quotient map from the algebra to its cotan with W. T is a cotan of a group G, and W is the Weyl group. In the case that G is GLN or SLN, this map sends a matrix to its spectrum, the set of eigenvalues. And given a base curve C, a reductive group G, and a line bundle L and C, the total space is just the moduli space of L-valued G Higgs bundles on the curve. In the case of G is GLN, this just means a pair consisting of a vector bundle of rank n and a Higgs field. So the Higgs field is a map, is an endomorphism of V valued in some line bundle L, and L is usually taken to be the canonical class or the canonical bundle twisted by a bunch of points where the bunch of marked points. Yeah. So it's either KC or KCD, where D is the divisor of marked points, the punctures. So the base of this integrable system, you can think of it as global sections of L tensor T or W. L is the line bundle, T is the cotan, W is the Weyl group. So a point in the base determines the W-Galois cover, where you just forget the W. And that's called the camel cover. So it's a map C tilde to C, where W acts in C tilde and the quotient is C. It's just the inverse image where you forget the W. The choice of a representation of G maps the camel cover to a spectral cover. So it's, we'll call that C tilde sub rho, depends on the representation rho that you chose. So in the case of GLN and the standard representation, the camel cover is a cover of degree n factorial. The standard spectral cover is degree n. But they're equivalent data. One of them determines the other. Explicitly, you can write down what the base is, and it's a sum of global sections, or H0s, of powers of L. So R is the rank of the group. The DIs are the degrees of the G-invariant polynomials. So for GLN, it's just the numbers are I. For SLN, you just skip the first one. The quotient map from G to T with W applied to the Higgs field determines a family parameterized by the base curve of L-valued points of T with W. And this is the Hitchin map. So it takes a Higgs bundle, that's a V and a phi, and sends it to the point in B, which is basically the characteristic polynomial of that Higgs field. And that characteristic polynomial exactly gives you the equations of the spectral cover or the camel cover. So when L is a canonical bundle, Hitchin proved that this is a holomorphically symplectic manifold, and the map to B is Lagrangian. In the meromorphic case, the analogous result was proven by Markman and independently by Botachin. They proved that there's a Poisson structure on it, and you can completely determine the symplectic leaves that are given by as the inverse images of the adjoint orbits in the Lie algebra under the residue map. And we'll consider the tame case, which just means that the divisor D of poles is reduced. The points are distinct. So where this comes from is that four-dimensional superconformal field theories have been the subject of study for years. But recently, there's this class of S theories that has been explored, and this has close connection to the Hitchin system, as I explained. So the Coulomb branch associated to the four-dimensional theory can be described as the base of the Hitchin system. And the choice Villey algebra parameterizes the available six-dimensional theories, and then the curve and the marked points specify the particular compactification. So you take your phi to have a first-order pole at each of the punctures. And what really matters is the G conjugacy class to which each element A belongs. So A is the residue of phi at each of the points. That's what determines the symplectic leaf, for example. So we'll sometimes call this nilpotent orbit the Hitchin orbit. When G is not of type A, one needs to further enhance this using some discrete data. The reason is that you need to look at the centralizer of the element modulo the connected centralizer. So it's the group of connected components of the centralizer that comes into describing that's the additional data that you have to specify. In SLN, this group is always connected, so the quotient is trivial, and you don't have to worry about this extra discrete data. That's the main reason that I'm focusing on SLN in this talk. There is a lot of work that's done on other cases, especially the types D and E by Dissler and his collaborators. He has this machine that he calls Tinkertoys that studies them. The important thing for us is that the parameters on which the physics depends are exactly the Deligne-Mumford compactification of the moduli space. So MGN is the modular of curves of genus G with n-marked points. And MGN bar is the Deligne-Mumford compactification. So it turns out that exactly points of MGN bar parameterize allowed versions of the theory, or things in which you can compactify the six-dimensional theory. The most interesting thing is what happens when you start at the interior and you move to the boundary. So when you move to a boundary component, you get some weakly coupled gauge group where the gauge coupling is essentially the point in the upper half plane that goes to infinity, the local coordinate around the puncture. So so usually the group that occurs is the group you started with, but the phenomenon that I want to focus on is that there are cases where the weakly coupled gauge group is a proper subgroup H of G rather than the whole thing. This often corresponds to a surprising physical phenomenon that a certain superconformal field theory with group G is as dual to a superconformal field theory which can be described by a proper subgroup. And there's some non-Lagrangian matter that is coupled to it. And the first example was due to Argyris and Seiberg, and Gayotto interpreted it in terms of these class S theories. So what we show below is that the appearance of these smaller groups as the weakly coupled gauge groups can be understood using the Hitchin system on nodal curves, in other words, boundary points of the Deligne-Mumford compactification. And this gives a clear geometric picture of how the small group arise. And it leads to classification of the types of interesting nodes that you get. So let me say a few words about the nilpotent case, which is what I was calling the unipotent case before. We work with the Hitchin system for SLN on a smooth curve C, and later on we'll allow it to degenerate. So we have a smooth curve C with a bunch of marked points pk. Nilpotent orbit is specified by its Hitchin partition or the dual lamp partition. So the Hitchin partition is just the sizes of the blocks. That's roughly what I was calling the U partition, in what Simpson was calling the U partition. And the non-partition is the dual, which is the S partition. So Hitchin and num orbits in SL4, it's 0 orders of phi k corresponding to them. So here's an example. So in SL4, if you're dealing with the unipotent or nilpotent case, so you don't have a bunch of partitions, you have just one partition. So the partition into Jordan blocks can be 4 or 3-1 or 2-2 or 2-1-1. And I guess I should have included the last one, which is 1-1-1-1. But that gives trivial physics, so I omitted it. The non-partition is the dual one. So if this is a 4, this is 4-1. This is 3-1, this is 2 and 2 1s, and so on. And since we're in SL4, the invariants in degrees 2 and 3 and 4. So the coefficients of the spiral cover correspond to a quadratic differential, a cubic differential, and a quadruple differential. And the fact that the matrix is nilpotent says that these things have to vanish to various orders. And you can work out some algorithms for calculating the orders, and I display the result. So the spiral curve is equation W to the n equals summation AI W to the n minus I. The AI is some pluridifferential in C. You know, there's a section of KC to the I. It has a allowed pole of order less than or equal to pi I. If you didn't impose the nilpotent condition, the order pi I would just be I. You're just allowing KC. The holomorphic differential will have a first order pole, and the I-tuple differential will have an ith order pole. But making it nilpotent will say that pi I is strictly less than I. And alternatively, there's a section with, so instead of specifying the order of a pole as the holomorphic section, you can start with the meromorphic section and impose a pole of order chi I. So pi and chi I add up to I. For a given nilpotent orbit, instead of pk, the order of the pole. So here's the algorithm. It's the row number containing I in the num diagram. So you look at the Young diagram, you look for the number I, and you count which row it is, and that tells you the order of the vanishing, or the order. I'm sorry, the order of the pole. And the complementary number, the order of the vanishing is I minus that. So, for example, the nilpotent orbit, as we saw, gives all the chi's equal to 1. The subregular orbit gives all of them 1 except for the last one, which is 2. And at the opposite extreme, the 0 orbit gives all the orders of vanishing are maximal. So another way of saying it is that the coefficient A is a section of some line bundle. The degree of the line bundle is 2g minus 2 plus the degree of d. That's for a single differential. For an I-tuple differential, you multiply by I. Then you correct it by subtracting the orders of vanishing. Sorry, something happened here, but instead of subtracting the orders of the vanishing, of course, you can get some other quantity and add the order of the pole. So the base of the Hitchin's fibration is the sum of the space of sections of all these bundles. So clearly the dimension of each of these spaces, by Riemann-Roch, it's at least d minus g plus 1, where d is this number. And of course, it's also at least 0. So the key definition for the rest of the talk is we say that this Hitchin system is okay if equality holds. In other words, if these line bundles are non-special, or again, that means that you're allowing an H0 or an H1, but not both. You don't want both H0 and H1 to be positive. That says that either H0 is 0, or H0 is given by the Riemann-Roch prediction because H1 is 0. So the history is that the physicists have this more complicated trichotomy of the good, the bad, and the ugly theories. And since we don't need them to distinguish the good and the ugly, we just coined the word okay for not bad. So we figured if they can refer to one cowboy movie, we can refer to the gunfight at the OK Corral for the property that we want. So basically, a system is okay if all the line bundles that arise from it are non-special in the sense of algebraic geometry. Okay, so that was the story for a smooth curve. Of course, we can easily replace the curve C by any Gorenstein curve. So as long as there is a good canonical line bundle, we can still make sense of the Hitchin system. Any curve that is devised on a smooth surface will do. But we're going to consider only curves that have nodes, because we're looking at points of the Deligne-Mumford compactification. So sections of the canonical bundle are just one forms on the normalization, with first order poles and opposite residues at the nodes. As in the smooth case, one can consider a GIT version. But as in the smooth case, the Hitchin system for C in a reductive group G is the space of Higgs bundles with KC valued Higgs fields. So it's just a pair of V phi. V is a G bundle, and phi is a K twisted endomorphism, where K is this canonical bundle of the singular curve. So as in the smooth case, you can consider either the GIT quotient and you get a nice geometric moduli space, or you can consider all Higgs bundles and you get a stacky object. And both of them are important. So also as in the smooth case, the spiral curve of a Higgs pair is the curve in the total space of the canonical bundle defined by the vanishing of the characteristic polynomial of the endomorphism. Hitchin base is defined to be the space of all spectral curves, so it's a direct sum of global sections of KC to the I. This is the unpunctured case. And there's a natural analog allowing Poisson divisor D just as before. So when the Hitchin orbits at the punctures are sufficiently big, we get a node that is not restricted in any way. We call such a node the standard node. So in some cases, for example, if the group is SL2 or if the genus is strictly positive, it turns out that every node is standard node. There are no exceptions. But if you go to small cases, for example, take P1 with 4 punctures and consider a separating node. So that means you take your curve, which is a conic, degenerate it to a pair of lines, and let's say you take 2 of the points to go to the left and 2 of the points to go to the right. So we're going to see an example where some of the Hitchin orbits are small, the resulting node is restricted or non-standard. So what that means is that we have a singular curve, we have a bunch of punctures that are smooth points away from the nodes. We're restricting the types of singularities we get at those nodes. We're restricting them to lie in some conjugacy classes. And magically, the result is that it imposes conditions at the nodes, even though we didn't impose them by hand, they just came out. So by making the conjugacy classes at the marked points small enough, you put enough restrictions on the Hitchin system that it forces special behavior at the node. And our claim is that that is what explains this physics phenomenon where sometimes the weakly coupled group H is strictly smaller than G. So we have to consider the generation of the Hitchin system. Consider a one parameter degeneration, of course, CT degenerating to a limit that is nodal. And then the question is, do the Hitchin systems fit together? So let's consider this case where you have a smooth curve that is a conic degenerating to a pair of lines, one on the left, one on the right, intersecting transversely at a point. And some of the points go to the left, some of the points go to the right. We'll consider the case with 4 points in the smooth case, 2 in each component in the limiting case. So a sufficient condition for flatness of this family of Hitchin systems is that the basic line bundle, so it's K of the base curve twisted by D, needs to be ample on the limiting base curve. Then it turns out that the Poisson Hitchin system is a flat limit of the Hitchin systems from the interior. So it holds for the whole Poisson system, and in particular, it holds for each symplectic leaf. So in our case, it just says that since the canonical class of a nodal curve consisting of 2 components is O of -1 glued to O of -1, you need at least 2 points on each of the components. So we are going to, so whenever we have a breaking of the curve into 2 components, let's say left and right, we will introduce a corresponding break of the Hitchin base into stuff that lives on the left, stuff that lives on the right, and a bigger stuff that we'll say lives at the puncture. So let L be the limiting bundle in the reducible curve. So we have a left version and the right version. Those are the restriction to 1 component at a time. And we let B sub L be the subspace of the limit B0, parameterizing those spiral curves whose coefficients vanish on the right. And similarly, we'll let BR be the subspace of spiral curves whose coefficients vanish on the left. So BL and BR are subspaces of B0. And whatever is missing, so B0 modulo the sum of B left and B right, we'll call that B center. So that's the stuff that's supported at the point. So we have these spaces, and we can take the dimensions. So the dimension on the left is going to be the maximum of the degree on the left, or 0. Similarly on the right. And then whatever is left turns out to be either 0-dimensional or 1-dimensional. Turns out to be 1-dimensional if both DL and DR is greater than or equal to 0. And in any other case, it turns out to be 0. So the primes here mean that these are the ones that we get on the singular curve. The unprimed things would be the things that you get as limits coming from the interior. And the question is, are these equal? So you may as well consider a slightly more general case, which is where there's no Hitchin system. You just have family of curves degenerate into a nodal curve in a line bundle, specializing to a line bundle on the singular thing. And you play with this short exact sequence. You take the line bundle and the limit, you restrict it to the right. The kernel is almost what you have in the left. It just, you're also imposing as an extra 0 at the intersection point. So you get degree 1 less for the kernel. So we see that the limit can be a proper subspace of the global sections. But that only happens when the line bundle on the left, one of them, either the one on the left or the one on the right, has higher cohomology, because it has to come from the coboundary map for this short exact sequence. So the condition is necessary and sufficient when a knot itself has no higher cohomology. And you can give an explicit example where you do some calculations, and maybe in the interest of time, I'll skip them. But you get, in this particular case where you have this type at the points on the left and this complementary type at the points on the right, turns out that the degree on the left is, for the degree 4 invariant, is -2. So the occurrence of this -2 tells you that it's no longer going to be non-special. It will be special. It will have a non-trivial H1, and that's going to be responsible for everything that happens. So the prime thing has dimension 2, but you calculate the unprimed thing, and it turns out we have dimension 1. So this is the simplest example where there's actually a discrepancy between the limiting dimension and the dimension at the center. So from the above example, you see that in order for the Hitchin basis to fit in a flat family, the naive line bundles need to be modified so as to eliminate the higher cohomology. And this turns out to be the only obstruction. So if C bar is the universal curve over the Deligne-Mumford convectification, we can describe a global modification of these line bundles. So let LK be the line bundle whose fiber at a given marked curve is canonical bundle of the curve, twisted by the poles. You raise it to the kth power, and you subtract a multiple of the pi, a linear combination of the points pi, where chi is the order of vanishing imposed by the specified nilpotent orbit. So that's the thing that I showed you in that table a few pages back. In the Deligne-Mumford convectification, we know what the bounded components are. So every partition of the set of marked point into two complementary sets, S and S complement, gives you a boundary divisor where you're looking at all reducible curves, CS and CS dual. Those are what I was calling C left and C right, such that the points of S go in the limit to this component, while the points in the complement go to the other component. And turns out, for some technical reasons, this only matters if the genus is 0. So the modification is you take LK and you subtract all boundary divisors of the Deligne-Mumford convectifications, each of them with the appropriate multiplicity, where the appropriate multiplicity is either 0 or k minus 1 minus summation of these quantities. It's basically H1 of LK evaluated on one of the two curves. So we have some universal formulas that tell you how to modify the line bundle LK to a line bundle LK prime. And the theorem is that the family of SLN Hitchin bases gives you a vector bundle over the entire Deligne-Mumford quantification. So with this modification of the L's to L primes, it allows us in a canonical way to extend the family of Hitchin systems over the base to a family over the compactified family. The argument is rather cultural. You take a reducible curve, you consider its branches, you look at the most wilted ones, you prune them away, you keep pruning until you get a healthy thing left at the end. And healthy means that it's obvious that the dimension is what it should be. I'm going to skip a little bit. I'll just point out that a new feature of allowing the singularity is that the Hitchin map fails to be proper in this case. So in the smooth case, I guess Hitchin proved that his integral system is proper, but the fibers here are not going to be compact. The basic problems in the Higgs field that the two branches of a node need to agree in order to be able to glue them. But they only need to agree in T mod W, which, as we now know, is not sufficient to say that they're conjugate, right? So T mod W basically describes something like sheets, or rather, it describes the semi-simple part of the conjugacy class, but it doesn't tell you anything about the Jordan blocks. So they can match T mod W, but they can fail to be conjugate. And that means that you will not be able to glue the thing on the right and the thing on the left to an actual Higgs field on the reducible curve. So work in progress would be to construct an appropriate partial compactification of Higgs so that the Hitchin map will extend to a proper object. The idea is that you have to replace the singular curves by some sort of semi-stable curves, where you replace each node by a chain of P1s. And along each chain of P1, along each P1 from the chain, you have a fixed conjugacy class on the interior, but at the 2 points where it meets the next curves, you're allowing the nilpotent to jump. And it's as far as we can tell, this seems to be sufficient information to completely compactify this Hitchin system. A similar construction has been carried out by Balaji, Barik, and Nagaraj in codimension 1 and for the group of type AN. We're trying to extend that to the full story. The other important thing that we get is that in an OK SLN Hitchin system, the numbers that you get, the degrees of the invariance, actually satisfy a pattern. They always correspond to the degrees of a group. So you get the group H, which is either SLK or symplectic group, from the pattern of orders of vanishings at those points, which is not at all obvious. We'd love to understand that more intrinsically, but here it's just basically a case-by-case analysis. So coming back to the Simpson story, in order to finish, so let's C be a point of the moduli space. Let's say 0, n+1 punctures with specified nilpotent residues and at least one of them regular. So Simpson showed that the irreducible character variety is non-empty if and only if these two numerical conditions hold. In this case, the number D, the difference between the sum of the dimensions and turns squared minus 1 turns out to be just the dimension of the character variety. Or by non-Abelian Hodge theory, it's the dimension of the Higgs moduli space. So one result that we have in this direction is that in this regular case, assuming that one of the residues is regular, Simpson's two conditions are exactly equivalent to the OK condition for our line bundles LK. In other words, the condition that comes from the physics that says that you get a good superconformal field theory exactly matches the condition that Simpson needs in order to prove existence of local systems. That's the regular case. So what happens otherwise? Well, in the regular case, demanding that the strongly parabolic Higgs bundle be OK is necessary and sufficient for the corresponding irreducible variety to be non-empty. And by non-Abelian Hodge theory, this is the same as non-emptiness of the corresponding moduli space of semi-stable Higgs bundles. The novel feature here is that semi-stability in the Higgs sense admits a translation to a condition of the line bundles LK appearing in the description of the Hitchin base. So now if we relax the assumption that one of the residues is regular, then Simpson's two conditions are known to be necessary, but definitely not sufficient. There are counterexamples in the literature. They're not sufficient for the non-emptiness of the character variety. But our conditions are stronger. So a natural guess might be that the OK condition on the line bundles, which is stronger than Simpson's condition in this case, might be sufficient. So is it sufficient to ensure the non-emptiness? For that matter, is it necessary and sufficient? We've done a bunch of numerical studies, and all the evidence we have so far suggests that this is true, but we're nowhere near being able to prove that. And since I'm basically out of time, maybe I will skip any other results. Let me just mention very quickly some of the important open questions in the area. So a key puzzle for physicists is the Coulomb branches of S-class theory decompose its hyperkähler quotients of projective Coulomb branches of limiting components. The group you need to divide by is often the full gauge group, but as we saw, it's sometimes a proper subgroup. We're giving an algorithm to determine which is the case, and if it's not the full thing, what the coupled gauge subgroup is. There's also a realization due to BFN, which counted this physics intuition as a hyperkähler quotient by the full group. So in other words, you can get the same hyperkähler quotient as a quotient by a full group and also as a quotient by a subgroup. And this, in individual cases, this gives very interesting coincidences of hyperkähler quotients. And we'd love to be able to understand that more intrinsically. Another interesting question is the structure of the base of the fibration on a symplectic leaf. In type A, our algorithm shows that this is always a vector space. In other types, we've done some experimentation and they suggested it should be a vector space, but there's no obvious reason for it. From the symplectic structure, you know that there's a flat structure on the base, but it's not clear why it has to be a vector space. So we conjecture that, but we cannot yet prove it. Next, we know how to identify the weakly coupled group H from its discrete data, which are the degrees of the Casimir, the Weil group action, etc. But it would be lovely to try to do an Nakajima type thing and not just describe the combinatorial stuff, but actually get the group itself to act on something. So we want to start with a spiral cover, spiral sheaf, and so on, and do some geometric construction that gives you this group H. And at the moment, we don't know how to do that. And the other question is, as I mentioned, we have the compactified family of Hitchin bases. We do not have the proper version of the Hitchin system. So thank you very much for your attention.
Thank you, Ron. We have time for questions or comments.
So there has been some conjecture of Simpson about connection between rigid and motivic representation. Does this give you more example of such a correspondences?
Well, so in the case that Simpson studied originally, that's a case where one of the classes is regular.
But this is for SL2 or SL3?
No. This is for SLA and for NEA.
Okay.
So he has this game of Simpson-Os, and he solves it completely using just combinatorial arguments. And using non-Abelian Hodge theory, he converts that to a solution. And then he's able to analyze all the rigid cases. And it turns out that there are 4 of them. There's one that corresponds to hypergeometric systems. There are 2 specific ones. I can show you if you want what they are. There are 2 specific ones, one for n even, one for n odd. N is the rank of SLN. And then there's one other specific case when n equals 6, which is exactly the one that I showed you. I don't have that page in front of me. But there's one example in rank 6, and that's a complete list of rigid cases when one of the classes is regular. Now, all the other known rigid examples are obtained by different techniques like Nick Katz's middle convolution and things like that. And those do not have a regular class. All the classes are non-regular. So what we're hoping is that our machinery coming out of the physics will be able to classify all of those, roughly extending what Simpson did with the regular assumption.
But
So
there will be many more cases.
So we hope to find out cases, but we don't have any yet.
But so from this perspective, the example of Hilbert modular surface, which appears already in SL2, in which case is it that you have mentioned? Which of these 4 cases is this example?
Yeah, I'm not sure, but I think that is an example where you do not have a regular class, so it would not be among the examples.
I see. Okay.
It makes it having a regular class.
I see.
Basically tells you that if you move that class to the other side, you want the map from the product of the n-1 other conjugates to classes to be dominant onto the group, because the regular classes are dense. And that's the key simplification that he uses. The interesting examples with arithmetic flavor are not of that type.
Okay.
So we hope to be able to analyze them using these modified Hitchin
Yeah, yeah,
system.
I understood that. I understood that. Yeah.
Yeah.
Very nice.
Yeah.
Thanks
question?
everyone for participating, and hope next time we see each other in IMSA in Miami.
That'll be nice.
Not on Zoom, I hope.
Any other questions for Ron? If not, again, thank you, Ron, for
Thank you.
very interesting talk, and thank all of you for joining us today. And I guess, Ludmila, that pretty much concludes this workshop, right?
Yep. I hope we see you in Miami in the fall, but this time in person, not on Zoom.
Yeah. Okay.
Thank you, everybody. Bye-bye.
Stay safe.
Bye-bye.
Bye.
Thank you very much.